F1 or Formula One is a motor racing sport which is based entirely on physics. Physics plays a fundamental role in F1 racing. The cars are designed entirely on aerodynamics. A Formula One car is essentially a physics laboratory on four wheels, except it goes at crazy speed and is more exciting. The main goal of F1 is to drive as fast as you can. They do this by creating an abundance of downforce while also minimizing drag. Newton's law in F1. First law. A car in straight line motion at a constant speed will keep such speed until acted on by an external force. The reason that a car does not coast to neutral is because of friction. An external force will slow the car down. In F1, friction comes from the tires and the air flowing over the car. Second law, F equals ma, where F is a force, m is the mass of the car, and a is the acceleration. This equation explains why the cars are light. The heavier car reacts slower to forces. The more F and less m, the more a. Why do F1 cars go so fast? F1 cars can go up to top speeds of 400 kilometers per hour. There are two main contributors to these. One, drag, and two, downforce. These cars are used to utilize these factors. Drag. Controlling how air flows around the car is crucial for maximizing speed and minimizing drag. So, what is drag? Drag is a force acting on an object in the opposite direction in relation to the acceleration of the car. The cars are designed so the airflow is as close as possible to the chassis or base of the vehicle. Drag happens in the opposite direction of the airflow. The wings in the front are specifically planned to direct the dirty airflow around the tires and create vortices. What are vortices? Vortices are spirals of air which separates airflow. Overall, vortices reduce drag. Drag reduction system, or DRS. If you have ever watched an F1 race before, you may have heard the announcer say, DRS zone now activated. As well, on the side of the screen, there is typically a section that tells you how far until the driver reaches DRS. DRS zones are enabled when the driver is 1 second away from the other driver. DRS zones allow the driver to go faster and have an advantage over this other driver. But what exactly is the drag reduction system? With just a push of the button, a back part of the rear wing flips open. This flap being open causes the car to speed up quite significantly. As seen in the photo, on the top, DRS is inactivated since the rear wing flap is closed, although on the bottom, drag is enabled by the flap being open. When a driver activates the DRS, the car goes about 15 kilometers per hour more on the straightaway. The DRS plays a great role of any race because when enabled, this extra speed allows drivers to overtake their opponent. Here's a quick video to really show the significance and importance of DRS.
Perez could do, or was it? Perez with DRS is coming back into turn 9.
Can Perez make it into turn 9? He saved up a bit of energy from that battery store, and with a bit of DRS possibly as well, has blasted past Lewis Hamilton.
As you can see in the video, Sergio Perez, the second driver, is behind Lewis Hamilton. Once he gets in the 1 second range, you can see how his rear wing flap opens. With the positive effect of DRS, Perez is able to pass the driver that was once ahead, Lewis Hamilton. Once Sergio is ahead, his rear wing flap closes. When the drag is closed, it increases downforce, but when allowed to be open, it decreases drag. This goes back to our equation on less drag equals more speed. The drag reduction system of DRS is a flap when closed increases downforce and when allowed to be open creates less drag, giving about 15 kilometers per hour of higher speed. Now that we have an understanding of drag and DRS, we will now be learning about another critical aspect of the aerodynamics behind an F1 car, downforce. To fully understand downforce, we must first understand the concept of the Bernoulli effect. The Bernoulli effect states that if a fluid, gas or liquid, flows around an object at different speeds, the slower moving fluid will exert more pressure than the faster moving fluid on the object. The object will then be forced towards the faster moving fluid. The Bernoulli effect is the reasoning behind an airplane's wing's aerodynamics. The shape of an airplane wing is so that the moving air on top of the wing moves faster than the air below it. Since air pressure under the wing is larger than the air above the wing, lift is produced. Now, how does this apply to F1? F1 uses the same Bernoulli principle to their cars. If you have ever seen an F1 car, you would notice that the F1 wings look similar to the airplane wings. The air moving beneath the car is moving faster than the air above the car. This creates downforce. The wings are shaped upside down, this producing a downforce instead of a lift. Downforce in an F1 car is essentially a negative lift. This is also why F1 drivers are sometimes called pilots. The large rear wing creates downforce, meaning it pulls the car back to the ground to overall increase grip levels. This is the reason that F1 cars look like they are super glued to the track surface. More grip means you can go faster. An F1 driver generates so much downforce that it can drive upside down on the ceiling or can drive on the roof of a tunnel. The amount of downforce on an F1 car is more than the car's weight, meaning the car is sticking to the road so well that when a driver is driving through the corners, the driver may face 5 Gs or 5 times the pull of gravity. Suddenly, the driver that weighed 154 pounds now weighs 771 pounds. The downforce at high speeds can be up to 1.5 tons. Driving with this much downforce can be like driving with an elephant on top of your car. Downforce is a necessity to maintain high speeds. More downforce equals more grip, faster corner speeds, and improved performance of the car. F1 is the fastest sport in the world, so now the next time you watch a Formula 1 race, you can fully understand why the cars are moving so fast. And if you've never watched an F1 race, I highly recommend you try.